Water is important in creating the pH of a substance. So when water is in solution, two important reactions happen. The first one is that some of those water molecules will dissociate, meaning they will break down into two different ions. You have OH minus, or the hydroxide ion. You will also have an H plus, or a proton. Some of these protons will then bind to other water molecules. So if you have an H plus molecule binding to an H2O, that would then form H3O plus, or the hydronium ion. Remember that H plus can be attracted to the slightly negative region of oxygen, and that's why it would form that hydronium ion. Now, the hydronium ion is very rare, but it is extremely important in reactions. They're considered to be very reactive with other substances, and these two reactions help to establish the acid-base reactions in aqueous solutions. When you see the pH scale, you may see the pH being referred to as the hydrogen ion concentration, or H plus. You may also see it being referred to as H3O plus. Now, both of these are interchangeable, but for the sake of our textbook and testing purposes, we simply refer to it as pH, referring to the hydrogen ion concentration. This slide depicts water and the pH scale. So water provides, once again, that basis for the dissociation of water provides a basis for the pH scale. And we know that the pH of a solution is going to be dependent on the concentration of hydrogen ions. Specifically, pH equals negative log base 10 of the concentration of hydrogen ions. This will be presented in molarity, and that refers to the number of moles per liter. We also know that when you have the concentration of hydrogen ions and you multiply it by the concentration of hydroxide ions, you should get 1 times 10 to the minus 14. This establishes the base of the pH scale. So the pH scale runs from 0 to 14, with 0 being most acidic and 14 being the most basic. To help you remember what is acid versus the base, I would suggest that on the acidic scale, you put in the term HCl. That's an example of a strong acid. And up at the top of the pH scale, where it says basic, I suggest that you put NaOH. This will help you to remember what's going on with the hydrogen and hydroxide ion concentration. So within this pH scale, you should be able to glean 4 important things. And when working with pH calculations, you should be able to equally exchange any of these values, which means that if I give you a pH, you should be able to give me the concentration of hydrogen ions, the pOH, and the concentration of hydroxide ions. So the pH runs from 0 to 14, and if you see on the scale, you also have what concentration of hydrogen ions that pH corresponds to. And remember, pH is calculated according to the formula. pH is negative log base 10 of the concentration of hydrogen ions. So what does that mean? In pure water, that means that my concentration of hydrogen ions would be 10 to the minus 7, because in pure water, I have a pH of 7. To give another example, if I had a pH of 6, I would know that my concentration of hydrogen ions is 1 times 10 to the minus 6 molars, or moles per liter. I can also get an indication of what my concentration of hydroxide is, and that's because, according to the formula, if we know what our concentration of hydrogen ion is, we know that we need to multiply it by the concentration of hydroxide to get 1 times 10 to the minus 14. So that means the exponents of those values should add up to minus 14 when you put them in scientific notation of 1 times 10 to the something. So if I have a hydrogen ion concentration of 10 to the minus 7, that means my concentration of hydroxide ions should also be 1 times 10 to the minus 7. Because if you add up those exponents, 10 to the minus 7 multiplied by 10 to the minus 7, you get 10 to the minus 14, which is just according to that second formula stated on this slide. That also means that the POH would be 7 as well. And this corresponds to a neutral solution. So if I have a pH of 7, then the concentration of hydrogen ions is 10 to the minus 7. The concentration of hydroxide ions is also 10 to the minus 7. So they equal each other. By definition, this is neutral. Neutral means the concentration of hydrogen ions equals the concentration of hydroxide. If the concentration of hydrogen ions is greater than hydroxide, this is considered to be an acid. And take a look at the pH scale here. As we drop down in pH, so if we go from 7 to 6 to 5 to 4, you can see that the concentration of hydrogen ions increases from 10 to the minus 7 to 10 to the minus 6, 10 to the minus 5, and 10 to the minus 4. So it may be deceiving because you're going from -6 to -5 to -4, but remember, these are expressed in scientific notation. So these are equivalent to 1 times 10 to the negative. So as the exponent gets smaller, the number actually gets larger. If, on the other hand, the hydrogen ion concentration is less than hydroxide, this would be considered a base. So let's do an example of this. Remember that when you have the concentration of hydrogen ions and you multiply it by hydroxide, you should get 1 times 10 to the negative 14. Remember, when you multiply numbers that have the same base, you're simply adding those exponents. Similar to if I had x squared multiplied by x to the third, I would end up with x to the fifth. That's the exact same principle we see here. So if I have 1 times 10 to the minus 4 times 1 times 10 to the minus 10, I would end up with 1 times 10 to the minus 14. If I have 3 times 10 to the minus 5 times 1 times 10 to the minus 7, I would end up with 3 times 10 to the minus 12. We're simply adding -5 and -7. When we are going from concentration to pH, we are taking the log of a number. Log will simply refer to the exponent. So what log will do when you have a base of 10 and you're taking the log of something in the format of 1 times 10 to the something, the log will get that exponent and basically cancel out that 1 times 10 to the. So log refers to the exponent only. When we're taking pH, remember we are taking the minus log. So that means by taking the negative log, we're taking that exponent, we're bringing it down, but we are also taking the negative log. So that means that if we're taking that number down and it's negative, it would actually turn positive. So some examples. If I had negative log of 1 times 10 to the minus 5, that would equal 5. If I was taking the negative log of 1 times 10 to the negative 11, that would equal 11. Conversely, if I didn't know the concentration of something, but I knew that the answer was 4, I can also work backwards. So that question mark would mean that I would have to take the log of 1 times 10 to the minus 4. Let's do some more pH practice questions. Like I said earlier, you should be able to easily calculate what the pH, POH, concentration of hydrogen, and concentration of hydroxide ions are in a solution if I am giving you one of these variables. So if you know that the pH of a solution is 8, how do you know what the concentration of hydrogen ions are in that solution? Remember, pH is negative log of the concentration. So if the pH is 8, that means that my concentration of hydrogen ions must be 1 times 10 to the minus 8 molar, or simply 10 to the minus 8. Would you consider the solution to be an acid or a base? If the pH is 8, it is above 7, so I would consider this to be a base. Similarly, what is the concentration of hydroxide ions? So if we know the concentration of hydrogen ions, we should be able to easily figure that out. If my concentration of hydrogen ions is 1 times 10 to the minus 8, that means my concentration of hydroxide ions must be 1 times 10 to the minus 6. Why? Because minus 8 plus minus 6 should add up to minus 14. I could also ask you what would be the pOH of this solution. And you can either get that by taking the pOH of the hydroxide ion concentration. So you could take 10 to the minus 6, take the minus log of that, you would get a pOH of 6. I could also take a look at the pH, which is 8, and the pH plus the pOH should equal 14. So if my pH is 8, my pOH should be 6. 8 plus 6 equals 14. Another example, what if I knew my hydrogen ion concentration was 10 to the minus 2? What would be my pH? The answer to this would be 2. Take the negative log, we take that exponent, we bring it down, and we also turn it positive. If my pH is 2, is this considered to be an acid or a base? If the pH is less than 7, this would be considered an acid. What is the concentration of hydroxide ions in this solution? That would be 1 times 10 to the minus 12. I could also ask you what is the pOH of this, and that would be 12. So my pH is 2, my pOH is 12, my concentration of hydrogen is 10 to the minus 2, my concentration of hydroxide is 10 to the minus 12. One last example, if the concentration of hydroxide is 10 to the minus 9, what is the pH? Remember, this is now indirectly. You have to indirectly calculate this. So let's work through it. If my concentration of hydroxide is 10 to the minus 9, that means that my pOH should be 9. 9 plus something, my pH, has to equal 14, so that means that my pH should be 5. I could also get it by working through the concentration of the ions. So if my concentration of hydroxide is 1 times 10 to the minus 9, I know my concentration of hydrogen should be 1 times 10 to the minus 5, and I know that pH is negative log of the concentration of hydrogen, so I would take the negative log of that value, and I would end up with a pH of 5. No matter what you're comfortable with, it doesn't really matter how you calculate these values, but you should be able to work freely through all of these: pH, pOH, concentration of hydrogen, and concentration of hydroxide. So we are going to end this topic by talking about acids and bases. So what is an acid? An acid is something that overall increases the hydrogen ion concentration. Remember that the hydrogen ion concentration is inversely related to the hydroxide ion concentration. So if my hydrogen ion concentration is increasing, that means that my hydroxide ion concentration would be decreasing. An acid is something that, because it is increasing the hydrogen ion concentration, it will tend to lower the pH of a solution. A base is something that increases the hydroxide ion concentration, and thus would lower the hydrogen ion concentration. So a base is something that would raise the pH. So this is why I suggested that when you look at your pH scale, when you get down to the acid in the lower part of the scale, you should put HCl. That will help you to understand what is happening. So as you work towards a strong acid, you are going to be increasing the hydrogen ion concentration. At the top of the scale, where you have your base, if you put NaOH, this will help you to remember that as you increase your pH and you get more basic, you are increasing your hydroxide ion concentration. When you have a strong acid or a strong base, that means that that compound is going to completely dissociate when it's put in an aqueous solution. If we take HCl, for instance, when it completely dissociates in a solution, it will completely break down into its ionic component, meaning that it will release H plus and Cl minus. When you have a strong base such as sodium hydroxide, it is going to behave similarly and break down into its ion components, so it will be releasing sodium ions as well as hydroxide ions. So these would be equivalent to things that are within the bottom and top range of that pH scale. You may also have weak acids or weak bases, and these molecules do not completely break down in solution. They do not completely dissociate. So if I had a weak acid, such as H2CO3 or carbonic acid, when I put this in aqueous solution, it would only partially break down. which means that one proton would be released, but the other hydrogen would still stay with the carbonate ion. So this would form bicarbonate HCO3 minus. We can also have a weak base, as seen here, and when NH3 is in solution, it will bind to the H plus ions that are in when water breaks down, and this will form the ammonium ion NH4. So these weak acid and weak base reactions are very important when you consider the role of buffers, especially the role of buffers in biological systems. So a buffer is something that will resist pH changes in solution. How it does this is by either absorbing or donating hydrogen ions. When you take a look at buffers, buffers are usually a combination of a weak acid and its conjugate base, or vice versa, a weak base and its conjugate acid. It's important to note that a buffer keeps things within a pH range. Do not get confused in thinking that a buffer keeps things neutral. That is not always the case. You can have buffers that keep things within a pH range of, say, 2 or 3. Similarly, you can have buffers that keep things in a range of pH of 10, for instance. So it doesn't mean that they neutralize something. They are simply there to keep things within a pH range. And that is referred to as their buffer capacity. So an important biological example of a buffer is H2CO3. We know that H2CO3, or carbonic acid, is a weak acid. So it will not completely dissociate. It will partially dissociate and partially break down in solution to H plus and HCO3 minus. So this is important in blood because this is an important buffering agent. Blood has to be kept within a pH of about 7.4. And one of the ways in which it can do that is by having carbonic acid flowing around in the bloodstream. Remember that we are constantly breathing in oxygen and releasing carbon dioxide as a byproduct, which can make the blood become very acidic. So by having carbonic acid, we can keep the pH within a range of 7.4, which is very important for cellular health. Carbonic acid is very resistant to change, and being a buffer, it can easily go and switch between carbonic acid and producing the bicarbonate ion. So let's take, for instance, an example. Let's say that our pH in our blood was all of a sudden lowering. So we had a lower pH. It's going from 7.4 to 7 to 6.8. And what is happening as the pH lowers? Remember, as the pH is lowering of a solution, the concentration of hydrogen ions is actually getting larger. What that means is that I will have excess protons in solution. So take a look back at the equation for carbonic acid and how it flows between H2CO3 and partially dissociates to H plus and HCO3 minus. You will see that there's two arrows representing that this equation can be driven in either direction. So if I have excess protons, if my pH is lowering too much, that means that in order to come back up to the proper range, I need to absorb protons. So that means that carbonic acid as a buffer will be driven towards the left. So those excess protons are going to be absorbed by the bicarbonate ion, and I am going to form H2CO3, or carbonic acid. In doing so, I'm going to take away those hydrogen ions from the solution, and as a result, my pH is going to start increasing and going back up. If you had the opposite effect, so let's say that my pH of my blood was getting more basic. My pH is all of a sudden at 7.8, it's at 8, it's at 8.2. How is this buffer going to deal with that? Remember, the equation can go either way. So that means that if my pH is increasing, that means that my concentration of hydrogen is getting smaller. So if I want to bring my pH back down, I'm going to have to add hydrogen ions to that solution. This equation can do so. As a blood buffer, the carbonic acid is going to dissociate into H plus and HCO3 minus, and by releasing those hydrogen ions, That will serve to bring the solution back down to the 7.4 pH. So by either releasing protons or absorbing them, the buffer can easily keep things within a range. And with that, that will conclude